Dum-de-dum. Gonna wait about one more minute and then I'll get started. All right, it's time for me to get started. I will start off with a brief announcement. So it came to my attention that they have removed some of the units from the AP Physics 1 exam. So they removed waves from the AP Physics 1 exam. They removed electric circuits from the AP Physics 1 exam. So, and I don't know if they're doing that just for this year or if it's just not on the AP Physics 1 exam anymore. But at any rate, I had already planned to talk about electric circuits, but I'm going to cut it short. So we're going to talk a little bit about electricity for about 3 lessons. Okay, so today, Friday, and then next Tuesday, we'll talk about electric circuits just because I already had those lessons planned. And then after that, we are going to start studying for the AP Physics 1 exam. So we'll have pretty much a full month to study. And so I'll be reviewing all of the content, and I'm going to kind of come at the content from a different point of view. So one of the things that the AP exam does is it presents you with experimental data. So we're going to be talking about the content from the perspective of experiments, and that'll also go well with when we go back to class. So we'll be able to do experiments in person, hopefully, and that should better prepare you, is my hope. So, but we're going to do 3 lessons on electricity. So, this is AP Physics 1. 6. Okay. So the first thing I'm going to talk about today is something called electric charge. Which is denoted by Q. Q is the variable for electric charge. And electric charge is a number much like mass. So it's like it's, you know, if you think about mass, it's like an attribute of the thing, okay? So charge is also, it's another attribute that different things have. And it describes how strongly something interacts electrically. Okay. So again, it's an attribute. So just like you have a mass, you have an electric charge. Okay. The units of electric charge are called coulombs, which is just abbreviated as C. So 1 coulomb of charge is a lot of charge. Charges are usually quite a bit less than 1 coulomb. But that's the unit we're sticking with. Oh my gosh. I'm tired today. Now, one of the ways that electric charge is different from mass is if we think about mass, the mass has to be positive. It can only have positive mass. Electric charge is a little bit different because charge can be positive, like a proton, for example, has positive electric charge. At least I hope you learned that in chemistry. Charge can be negative, such as an electron. Electrons have negative charges. Or it can even be 0. So there are things that have 0 electric charge. All right. And so it actually turns out that there is a fundamental amount of electric charge. By the way, sometimes I will say electric charge, other times I'll just say charge. It's the same thing, okay? So you might hear me drop the electric, but I'm just trying to say electric as much as I can in this lesson, okay? And so that fundamental charge is denoted by E, and it is equal to the charge of a proton, okay? And the charge of a proton in coulombs is plus 1.6 times 10 to the minus 19 coulombs. So usually when we're writing electric charges, even if it's positive, we still, with most numbers, like if I write 4, I don't need to write plus 4. It's assumed that it's a positive unless I put a negative sign in front of it, right? But with electric charge, usually you would put the plus in front, even if it's, the convention is you always put the sign of the charge in front. Okay, and so, anyways, excuse me. The charge of a proton is plus 1.6 times 10 to the minus 19 coulombs, which is also called E, plus E. The charge of an electron, on the other hand, is minus 1.6 times 10 to the minus 19 coulombs. So that is negative E worth of charge. All right. The charge of a neutron is 0 coulombs. So these are kind of like the building blocks of all matter. Okay, so if you imagine, let's imagine that you build something at the atomic level. So you build it by adding protons and neutrons and electrons. You add them. You're adding these things one at a time. Okay. And so if you can imagine the charge, imagine the total charge of that object as you're adding these things. Okay. Your total amount of charge is always going to be a multiple of E, right? Because you're built up Like, what if I have 5 protons and then 3 electrons? Okay, so my total amount of charge is going to be 5e minus, what did I say, 2 electrons minus 2e. So that would be 3e would be my charge. So the amount of fundamental charge that I have, I'm always going to have a whole number of fundamental charge, okay? And so that is called the quantization of charge, okay? It is impossible, so that's called the quantization of charge. And what it says is the total amount of charge on an object is always going to be an integer. So this is an integer times the fundamental charge. Integers can be negative too, remember, or 0 is an integer as well. So you could have a charge of negative 700e, but you couldn't have a charge of negative 700.5e because that isn't a whole number of charges, of fundamental charges, okay? So for example, if you could have a charge of 1.6 times 10 to the minus 19 coulombs, that is 1e of charge. You could have a charge of 3.2 times 10 to the minus 19 coulombs. Okay, that would be 2e of charge. You could have a charge of 0 coulombs. That is 0e of charge. You could have a charge of minus 4.8 times 10 to the minus 19 coulombs. That is negative 3e of charge. But you could not have a charge of 2.4 times 10 to the minus 19 coulombs. Why? Because that is actually 1.5 fundamental charges. Okay, so this is not possible by the quantization of charge. Okay, another thing we could think about is you could not have, like, let's say 0.8. Actually, let's say 0.4 times 10 to the minus 19 coulombs of charge is not possible. Okay? Because that would be, well, 0.4 is a quarter of 1.6. So this would be 0.25e. Again, that's not a whole number of fundamental charges. Okay? So we could think about E is the smallest amount, the smallest possible amount of positive charge. All right. And again, so there are deeper reasons than this, but at a simple level, that's because everything is built out of protons, neutrons, and electrons. Okay. So this leads me to the idea of net charge. Of composite objects. So a composite object is an object that's built up out of other stuff. So we're composite objects, right? We're built up out of cells, if you will. And then those cells are also composite objects because they're built up out of molecules, and those molecules are composite objects because they're built up out of atoms, and then those atoms are composite objects because they're built out of protons and neutrons and electrons. Okay? So if you have a composite object, the net charge on that object is simply the sum of the charges of the individual pieces that make up the composite object. Okay? So For example, the net charge of an atom is equal to 0 coulombs. Why? Because an atom has an equal number of protons and an equal than it does electrons, okay? So if you have, for example, carbon has 6 protons and 6 electrons. So the net charge of a carbon atom is going to be plus 6e minus 6e equals 0. Okay? So atoms have an equal number of positives and negatives. And then you are built up out of atoms. So your net charge is approximately 0. Now, the reason I say approximately is there are actions that you can do to actually give yourself a small net charge, right? If you rub your feet on the carpet, if you rub your feet across the carpet, you will basically add or remove electrons from your body, which will cause you to acquire a net charge. Also, sometimes if you use certain equipment, you can get a net charge. So, like sometimes I use a belt sander or a belt grinder, and I use it on metal. And occasionally I will zap myself after using that because of the friction generates charge. Okay. The net charge of an ion, however, if you remember from chemistry, an ion is an atom that has had electrons removed or it has had extra electrons added onto it. So the net charge of an ion is not going to be equal to 0. Okay? So I wanted to talk about conductors versus insulators. Conductors versus insulators. So these are, this is a way to classify materials. We can sort of broadly classify materials as either a conductor or an insulator. And so I guess I'll start with an insulator. If we think about an insulator, it's made up out of atoms. Okay? So here are the atoms. And those atoms have positively charged nuclei. Okay? And then each positively charged nuclei has electrons around it. Okay? And those electrons are in orbitals. They're in a cloud, if you will, electron cloud, an electron orbital, whatever you want to call it. And the electrons are stuck to one nucleus. The electrons are stuck to one nucleus. Okay? So that makes an insulator. Insulators tend to be made out of rubber, wood, ceramics. Okay. And one of the things that you want to notice is because the electrons are stuck to a single nucleus, the electrons cannot flow because they are stuck in place. But then you have materials like insulators, called conductors. And for a conductor, the electrons are free to roam. Through the material. Okay, so you still have the same number of electrons, but the electrons aren't stuck. So here I had 6 electrons, here I have 6 electrons. These electrons are just moving around. They're bumping into stuff. They are going all over the place. Okay, so these electrons are free to roam wherever they want to go. Okay, and so electrons can flow for a conductor. Conductors tend to be metallic. Also, liquids, if liquids have an ionic solid dissolved in them, so for example, water, if you put table salt, which is sodium chloride, into it, the sodium and the chlorine will dissociate, so you have an Na plus and a Cl, or is it an Na plus 2? I can't remember. I think it's an Na plus and a Cl minus, floating around in the solution. So now you have charge that can move around the solution. Okay, so conductors tend to be metal, or they tend to be liquids with dissolved ions. Okay, they can be conductors. Okay, so we've been talking about this flow of electrons. So what is the flow of electrons? There's a thing called electric current, which is, which is denoted by I. And it is a measure of the flow of charge. And usually that flow of charge is electrons. Okay, why is that? It's because if you have a material that's a conductor, the positively charged nuclei are stuck in place. It's the electrons that are bouncing around. Okay, so it's usually the electrons that are bouncing around. And so the current is equal to the amount of charge that flowed divided by the time it took for that charge to flow. Okay, so we could write that as current is charge divided by time. So this is kind of the equation definition of electric current. And so from this equation, we can get the units of electric current. Well, current is a charge divided by a time. Okay, and so current is going to be measured in units of charge divided by units of time. So that's going to be coulombs per second. All right. Now, this has a special name. A Coulomb per second is called an ampere, which is, usually not, people don't say ampere, they just say amps. And it's abbreviated A. So if you live in a house, maybe in your garage, maybe outside, it's possible, you probably have a breaker box. And on that breaker box, or in the breaker box, there's a bunch of switches. And the switches might say things like 5A, or 10A, or 15A, or 30A, or something like that. Okay? And so your house has, and even if you're living in an apartment, you still have this in your house, in your apartment. It's just that you don't have access to the breaker box. But your house has all of these electric circuits in it, and these electric circuits have a certain maximum amount of current that they can hold. Okay, so it might be 5 amps. Okay, so let's say I had 6 amps of current flowing in this circuit that has a maximum of 5 amps. Well, what will happen is if that happens for too long, the breaker will trip and it will cut the current flow in that circuit. Okay, so so basically the breaker box is there to provide safety. Okay, and it stops the current flow if it becomes too great. And different circuits have different amounts of current flow that will cause the breaker to trip. That's why it's called a breaker, right? It breaks the circuit. So why would you want to break the circuit? Well, it's because current is dangerous. For lots of reasons. Okay? So one of the reasons that electric current is dangerous is that if we let's imagine you have a wire which is made out of metal. Usually wires are made out of copper. Okay? So here are the copper nuclei. Okay? And if a wire is conducting current, that means that the negatively charged electrons are flowing through it. Okay? But what happens is as the electrons are flowing, they are bumping into stuff. Okay? So these electrons, they're flowing, they're bumping into stuff. And when the electron bumps into stuff, that causes the nuclei to vibrate. Okay? So those little collisions cause the nuclei to vibrate. And that vibration is what we perceive as heat. Okay? So that is heat. So basically, when electric current is flowing through something, it gets hot. Okay? So one of the reasons that electric current is dangerous is because it generates heat. Too much generates heat. Okay? So if you got struck by lightning, for example, then you are going to have burns because that electric current, those electrons that were flowing through you, bumped into the atoms in your body and caused them to start vibrating. That's heat. The other thing that's dangerous about it is your body communicates with electrical signals. Okay? So, for example, your heart is getting a signal from your brain to beat. Okay? If I move my fingers, my brain is sending signals to the muscles in my fingers to activate. Okay? It's an electrical signal that tells your muscles to do their thing. So, that's obviously really bad if you have electric current running through your body, because the electric current, your muscles aren't smart enough to distinguish an external electric current from the signal from your brain. Okay? So if you've ever noticed people who, if you've ever seen a video of someone being electrocuted, they're like frozen. They can't control their body. And the reason is that their brain is trying to control the body, but the brain is being overridden by those electrical signals, okay? So for example, what if this phone was, had a short circuit or something, and I could electrocute myself? Probably wouldn't electrocute me if I just had the phone by itself, but if it was plugged in, it could electrocute me. So if I touch it and it starts electrocuting me, the muscles in my hand are going to activate. And my mind could be telling my hand, let go, but my hand won't be able to let go because it's not my brain that's telling it to grip, it's the electricity coming off of the phone, the electric current that's flowing out of the phone. So I won't be able to let go. So that's very dangerous. I could be electrocuted and I wouldn't be able to remove myself from the situation, okay? If it interrupts your heart, it can cause your heart to stop. If you ever have to touch something that you think might electrocute you, you should avoid touching it if at all possible, but if you have to, I would always recommend touching it with the back of your hand first, because if it's going to electrocute you, and it electrocutes you, and you touch it with the back of your hand is going to grip like this. Because of the electricity, it's going to do something like this. And so that will pull you away from the object. And so you won't be electrocuted afterwards. If you decide to hold on to it and actually grip it, then once you start being electrocuted, you're not going to be able to let go. Okay? Another danger of electric current is you can have arcing. So if you have two conductors next to each other, or actually arcing happens when you have a break in the circuit, okay? So basically what happens is you have, here's your wire, okay, and then you have a gap, okay? And maybe an electron is flowing down the wire, and if there's any kind of a gap, it can actually jump the gap if the gap is small enough, which is called arcing, and then continue along its way. All right? This arc is very hot, and it can light things on fire. Okay? Of course, just the regular heat also can light things on fire, but arcing will. So actually, this happened. This happened to my dad's cabinet shop. Okay, so my dad, he sold his company, but he used to own a company that made kitchen cabinets. Okay, and you paint the cabinets. Customers want the cabinet doors painted with various colors, and so there's a room. It's the paint room. Okay, and there was an electrician working in the paint room. The electrician didn't turn the power off to the paint room and was working in it. And he brought two wires close to each other, and it arced. Okay, and that arc in a room filled with aerosolized paint particles basically burst into flames. And the guy, everyone had to run out of the room, and the entire room was up in flames in seconds. Okay, they had to call the fire department. So yeah, arcing is dangerous. One of the things I want to point out. I see there's a question in the chat about how do electric currents relate to defibrillators. Okay, so I'm not a medical expert, so I don't know that I can answer this 100% well. But so if your heart stops, I believe electric current will not help you. Okay. So if your heart stops, what they do is they give you a shot of adrenaline, essentially. Okay, and that is what wakes you up. But if your heart is having an irregular rhythm, they can use a defibrillator to sort of jolt it and snap it back into its regular rhythm. That, to my knowledge, that's how a defibrillator is used. So I believe, like, atrial fibrillation is the fibrillation is when your heart is beating erratically, and a defibrillator makes it not fibrillate anymore. One of the things I want to point out is that you can have charge or no charge with or without current. Okay? That's kind of a confusing sentence, so let me elaborate. So if you have positive charge that is at rest, okay, this is net charge. You have net charge, but you have no current. Okay? So you have charge, but there's no current because the charge isn't moving. You can have net charge and current. What if I have positive charges and those positive charges are moving? This is net charge, and we have current. All right, so we have moving positive charge, so we have net charge and current. It is possible. What if you have the positive nuclei, and then you have the electrons are flowing over the top of them? Okay, here you have, for every positive charge, you have a negative charge. So here you have no net charge because there's as many positives as there are negatives, but you do have current. All right. And then lastly, you could have negative charges that are at rest, and you have positive charges that are at rest. So this would be no net charge and no current. So you can have net charge and current are sort of independent of each other, depending on the structure of what's going on. Okay. All right. So what I wanted to talk about now is something called Coulomb's law. And this is the law for the electrical force between charges. So what we want, the picture we want to have in our heads is you have two charges. One of them is Q1, the other one is Q2. And those charges are separated by some distance, which we'll call big R. Okay? Then the force between those charges is going to be a constant called K times the absolute value of Q1 times Q2 divided by the distance between them squared. Okay? So this is called Coulomb's law, and it's a rule for calculating the size of the force between charges. K is a constant of nature. It is called the Coulomb constant. And its value is 9 times 10 to the 9th Newton meters squared per Coulomb squared. So it's a big number, 10 to the 9th. That's a billion. So it's 9 billion. Let's just look at the general properties of this equation, okay? So in particular, as R increases, that means that the charges are getting further apart. We can see that R is in the denominator of this equation, okay? And so if we make the denominator bigger, that makes the size of the force smaller. If we make the charges bigger, so as Q increases, Q is in the numerator. If we make the numerator of a fraction bigger, then the force will get bigger. And so this is actually motivates my definition of electric charge in words, because what did I say? I said electric charge is a number describing how strongly something interacts electrically. So what I meant by that is more charge means more electrical force. Okay? I also want to notice you guys to notice the absolute values here. Note the similarity in structure to the gravitational force. The gravitational force is big G m1 m2 over r squared. So see how they both have 1 over r squared? They both have the product of two attributes. Okay? So Q1 times Q2, M1 times M2. So we could think about mass as almost like gravitational charge. In some sense. Okay? Or we could think about charge as almost like gravitational mass. Or electrical mass, excuse me. Okay? So, yeah, so it's they're very similar in structure, but they have different constants of nature, okay? And then, of course, gravity can be only attractive, whereas electricity, as you probably know, can be attractive or repulsive, okay? So that leads me to my next part, which is, what about the direction of the force? Okay? Well, I'm pretty sure you already know the rule. The rule is opposites attract, and likes repel. Okay. Yeah. So if you have a positive charge next to a positive charge, they will repel each other because they are alike. If you have a negative charge next to a negative charge, they will repel each other because they are alike. If you have a positive next to a negative, they will attract. If you have a positive next to zero charge, nothing will happen. Because if one of the charges is zero, you have zero multiplying the force, so you get zero force. If you have a negative next to a zero charge, nothing happens. Okay, so I'm pretty sure you already knew about that. So again, the Coulomb's law tells you the size of the force, and then the whole opposites attract, likes repel tells you the direction of the force. Let's do an example just really quick, and then I'll be done. What is the force between an electron and a carbon nucleus separated by 3.4 times 10 to the minus 10 meters? Okay. So this distance is very small because we're talking about subatomic particles. We're talking about nuclei and electrons. Now, carbon has atomic number 6. So that means that the nucleus is going to have plus 6 fundamental charges. Okay? And then the electron, of course, has negative a fundamental charge. So to get the force, we do K, which is 9 times 10 to the 9, times the absolute value of Q1, negative 1.6 times 10 to the minus 19, times Q2, which is the carbon nucleus, so that's 6 times 1.6 times 10 to the minus 19, and that's a positive number. So the absolute value is going to get rid of that negative sign. Divided by 3.4 times 10 to the negative 10 squared. All right. And I worked this out last period. It is 1.2 times 10 to the negative 11 newtons. That is a very small amount of force, but electrons and nuclei are very light, and so that very small force is enough to accelerate those particles quite a bit. All right, that's my lesson for today, so we'll check in the Zoom room, and then I'll probably let you go a couple minutes early.